So, hello everyone, good evening. Welcome to this series of talks organized by the Institute of Computing here in University of Campinas, São Paulo, Brazil, and also by the Catholic University of Rio, the Department of Informatics, here represented today by Professor Marcus Endler, Director of the Institute there. And here, I'm currently the director. I'm Professor Anderson Rocha. And today we have the pleasure to host this talk on deep networks that are kernel machines by Professor Pedro Domingos. Pedro is Professor Emeritus of Computer Science and Engineering from UW. UW is the University of Washington in Seattle, US. He is best known for his great book, The Master Algorithm. Probably many of you have heard about this book before. And he has this kind of provocation today that deep networks are indeed kernel machines, which has some implications because kernel machines are basically geometric machines. And if that's true, let's see the consequences of that kind of representation. Pedro, thank you very much for accepting the invitation to give this talk today. Normally, we have 45, 50 minutes in terms of talk, and then 20, 25 minutes for questions. So I will stop sharing my screen now, and the stage is all yours. And I also thank the presence here today of Professor Marcus Endler. I will give him the word now to also thank you. Please go ahead, Marcus.
So, good evening to all of you, and thank you very much to Professor Pedro Domingos. It's an honor to have you in our joint seminars between Campinas and PUC-Rio, and I look forward to learn a bit more about deep networks and kernel machines. Thank you very much.
Thank you, Marcus. Pedro, thank you again. Please go ahead.
Okay, thanks for having me, and thank you, Anderson, for the introduction. Let me share my screen. Are you seeing my slides?
Yeah, it's perfect.
Okay, very good. So, as Anderson already alluded to, I'm going to talk about how deep networks are really kernel machines. And in fact, more generally, all models learned by gradient descent are kernel machines, which is a very surprising result, I would say, but also I think a very meaningful one in what it explains and in the implications that it has. And for those of you who have read the master algorithm, you know that the general agenda is to unify all the different learning paradigms under one umbrella, like the standard model in physics. And I think this is a significant step forward in that agenda. So the big selling point of deep learning, at least what first attracted me to it many years ago, has always been that it can discover new representations, right? You don't just have to hand engineer the features anymore. The features are learned by the algorithm itself. And this is potentially very, very powerful. And less work for the data scientist and so on. But how exactly these representations are discovered and what they are has always been very murky, right? There's some intuitions, but nothing formal, nothing very concrete, nothing mathematical. And so the goal of this work was to try to understand that a little bit better. And surprisingly, what came out of this was that actually deep networks are something that we know very well. They're just kernel machines with a particular type of kernel that I will talk about. A more powerful kernel than previous ones, so there is definitely an advance here. But in a way, the amount of feature discovery that is going on in deep networks is maybe less than we had assumed it would be. In some ways, that's bad news, but there's also some good news here. One is that, as we'll see, we can now interpret the weights of a deep network as just a superposition of the training examples in the kernel space of the kernel machine. So the deep network is now much more transparent. Like, it's not this big mess of weights that nobody understands what they mean anymore. We actually understand quite well what those weights mean at this point. And the architecture of the network in this framework plays a very useful and important role, which is the architecture is how we incorporate knowledge into the kernel of the kernel machine. And as we'll see, there are many other interesting implications of this for deep learning on the one hand, for kernel machines on the other, and also for other kinds of machine learning, maybe even more interestingly, as we'll see. So very brief review, and just to set some notation down. I'm sure you all know this. A kernel machine is a model of this form. Y is some optional nonlinearity applied to a sum over the training examples of a kernel between the test example X and the training example Xi. And the intuition is that the kernel is somehow in many different forms measures the similarity of the training instance and the test one, so that training instances that are closer to the test instance will play a bigger role in making a prediction for it. And so each of these has a weight, AI, and then there's also a constant B. And this is the model, right? So it's very simple at this level. The weights AI are learned, and typically those weights take the form of a weight times the predictive value, whether it's regression or classification. I did not put that here because I want this to be as general as possible. In particular, it also applies to nonlinear things like kernel PCA and whatnot. But typically, that AI does incorporate the predicted value, but that doesn't change our treatment in any significant way. So X is our query data point, the Xi's are the training data points, and B is another learned parameter. And gradient descent is learning by the following very simple method. This is, of course, just the most basic version of it. We initialize the weights typically to some set of random values, the weights of whatever model this might be, a deep network, or it could be anything else. So we initialize them to some random values, and then in each step, we subtract from the current weight vector some learning rate epsilon times the gradient of the loss function that we're optimizing with respect to the weights, right? And this talk is really just one theorem that shows that surprisingly these two things, even though they look very different, are essentially the same. And now in one direction, this is not new and not surprising. We already know that kernel machines can be viewed as deep networks or as neural networks that aren't deep with just one layer, and that layer is the kernel. So for example, kernel machines with Gaussian kernels are equivalent to radial basis function networks. So that we've known for a long time. And it's part of why deep networks have overtaken in most ways kernel machines. But in the other direction, the conventional wisdom is that deep networks are strictly more general than kernel machines, because there are functions that can be compactly represented using many layers that cannot be compactly represented using only one layer. So, if you want to convert a deep network with many layers to a kernel machine, you may suffer an exponential blowup, right? And there are theorems of various forms about this, and and they're true. So what gives? Well, what gives is that there's a difference between representation and learning. Certainly, the deep network representation is more general than the kernel machine representation. But just because you can represent something doesn't mean you're able to learn it. And as it turns out, the fact that you're learning by gradient descent, which is actually a very simple local, search procedure that is very limited, is actually a strong enough restriction that once you learn the deep networks with gradient descent, you wind up with, surprise, surprise, a kernel machine. So as long as the method that you're using to learn is gradient descent, it turns out the two are indeed equivalent. So let's see how that comes about. And the key object here that really this whole thing is centered around, and is also, I think, probably quite useful in many other ways in addition to this particular result, is the notion of a path kernel. And for those of you who are familiar with neural tangent kernels, which have become very popular in the last few years as a way of analyzing deep networks, a path kernel is the integral of the tangent kernel over the path that the weights trace during gradient descent, hence the name path kernel. If you don't know about neural tangent kernels, ignore what I just said, and here's what a path kernel is. A path kernel is the integral over the path taken by the weights during learning, or the sum if it's a discrete sequence of steps, but it's analytically more convenient and more elegant to think of it as an integral. So it's the integral over the path taken by the weights during learning of the dot product of the output of y, the variable that we're predicting, as a function of the input at the 2 points. So the dot product of the gradient of y at x and the dot product of the gradient of y at x prime integrated over the path is the kernel between x and x prime. Okay, so this is a little bit of a mouthful. Let's try to get more of an intuitive understanding of what this is doing. What the path kernel really doing is measuring how similarly the function varies at 2 points, the 2 points that we're comparing in the kernel. It measures how similarly the function varies in the 2 points over the course of learning. So here's a very simple example. The weight, we just have 2 weights, so the weight space is just the plane. And here's the path, a possible path taken by the weights during gradient descent from W0 to W1 all the way to W final. And at each point, I have the gradient of y with respect to x. X is my test example that I'm now trying to classify or predict a continuous value for. And I also have the gradient of y with the current weights for the training data points x1 and x2, right? And each of these is a vector in weight space, right? The gradient is a vector in weight space. And now what I'm going to do is I'm going to form the dot product of the gradient for x with the gradient for x1 and the gradient for x2. And if you notice over the course of learning here, the dot product of the black vector is on average larger than the dot product of the black vector with the blue one, which means that on average, the dot product of the gradient with respect to x is higher. So the gradient with respect to x is closer to the gradient with respect to x1 than to the gradient with respect to x2. Okay, and this means that by the path kernel, other things being equal, x1 will therefore have a bigger role in classifying x than x2 does, right? And so at the end of the day, what we have when we have the final trained deep network is a kernel machine with a kernel that is computed in this way. And as I mentioned, you know, if you're familiar with neural tangent kernels, you will immediately see the relationship here, right? The path kernel is just the integral of the neural tangent kernel. So let's, you know, get a little bit more formal and make this more precise. I'm going to just call the neural tangent kernel, or NTK, the tangent kernel, because there's actually nothing neural about it. This applies to any differentiable model. So I will say that the tangent kernel associated with the function f sub w of x and a particular parameter v is the following. So k sup g sub fv of x and x prime is just the dot product of the gradient of f of x at w and the gradient of f of x with respect to w and the gradient of f of x with respect to w at x and x prime, both taken at v. Okay, so remember the function depends on 2 things: x, the input, and w, the weights, and you got to keep those 2 things separate, right? So for example, in this case, you know, I'm taking the weight vector at a particular point v, but I'm considering 2 input vectors x and x prime that I want to compute the kernel between. Okay, so the gradients in this case are taken at v. And now the path kernel associated with the function fw of x and a curve c of t in parameter space is just the integral of the tangent kernel over that curve. So I let v vary over whatever path, and then I do the integral of that dot product over that path, and this is my path kernel. Okay. And now we can state the main theorem. It's slightly long-winded, but let me just state it first and then see what it means. And then actually the proof of this theorem is remarkably simple. In fact, it's surprising that people didn't think of this before, but I will actually be able to give you the sketch of the proof in just a few slides here. So here's the theorem. Suppose that you have a model y equals fw of x, where f is just a differentiable function of w, and it doesn't even have to be a differentiable function of x. It can be anything with respect to x. So it could be discrete. The x's could be discrete structures, for example, like text or graphs or whatever. And this model y equals fw of x is learned in the usual setting from a training set of pairs xi and yi star. So the star means that this is the real class of xi, or the real output value corresponding to xi. There's m of these training data points. We learn it by gradient descent with, as usual, a differentiable loss function that is a sum over the examples of the loss between yi star, the true class of the example, and yi, the predicted class. And we do it as usual with the learning rate of epsilon. Then the theorem says that in the limit of epsilon going to 0, y is just a kernel machine. It's the sum over the examples I of ai times the kernel between x and xi plus b. Okay. Now, what are these ai's and k's and b's? Of course, this is a big part of the theorem. It's not just the statement that that it has this form. So the k of x and xi is, as I mentioned, the path kernel associated with the function and the path taken by the parameters being gradient descent. ai, the weight corresponding to the ith example, is minus the average loss gradient with respect to yi along the path, weighted by the corresponding tangential kernel. The reason there's a minus here is just that we're minimizing the loss. If this was something that if it was an objective function that we're optimizing, it would be positive. And b is actually the initial model, right? So b is simply the initial neural network or model with random weights. Okay, so this might seem a little surprising, right? But actually, it's the derivation is very straightforward. So here's the derivation. So let's start by taking the limit as epsilon tends to 0, right? In other words, let's consider that the gradient descent steps are infinitesimally small, right? This is the standard way to analyze gradient descent, and it's very convenient. And we get what is called a gradient flow, right? A gradient flow is a differential equation for how the weight vector varies over time. It says that the derivative of the weight vector with respect to time is just minus the gradient of the loss function with respect to the weights. And if you're not familiar with gradient flows, you can see very easily where this equation comes from just by going back and looking at the expression for a step of gradient descent. And if you subtract ws, the weight at step s, from both sides, and then divide by epsilon, and let the epsilon goes to 0, and therefore the difference between the weights also go to 0, what you get on the left-hand side is the derivative of the weight vector, and on the right side you just have minus the gradient of the loss function, which is exactly the gradient flow equation, right? So we're just thinking of the gradient as if the weights continuously evolve over time from their starting point to their final optimum. Okay, and now so that's step 1. Step 2, we can apply the chain rule to the derivative of y, the output of the network, over time as the weights are learned, right? So this is just going to be the sum, right, over the dimension, over the number of weights of the derivative of y with respect to the weight times the derivative of the weight with respect to time, right? That's the chain rule. And so we can write this more compactly as the gradient of y, right? Notice that this vector here, is the gradient of y times the derivative of the weight vector with respect to t, and both of these are vectors of dimension d, and we're just doing the dot product. Okay, so now we can combine the two by replacing dw/dt with the gradient flow expression, and what we get is just minus the dot product of two gradients, the gradient of y and the gradient of the loss, both with respect to the weights. Notice that this is already starting to look a little bit like the result that we're looking for, even after just like these two very simple steps. So next step, let's take advantage of the additivity of the loss as we usually do, right? So I can decompose the loss into a sum of losses over the individual examples, by assumption, and all losses that we use have this property, right? And now what I get is, and then I can push that sum outside the dot product. So I just get that the derivative of y with respect to time is just minus the sum over the examples of the dot product of y, of the dot product of the gradient of y and the gradient of the loss with respect to the particular example, right? And now we can apply the chain rule again to the gradient of Li, which turns that into the derivative of Li with respect to y. I'm calling that L prime I. And now the gradient of y with respect to the weights, okay? Notice that now at this point, we already have here a dot product of the two gradients that we're interested in, right? So the tangent kernel is now showing its face here, okay? Now, we know dy dt, so we can compute y by integration, right? So y, which is the output that we're interested in, the output of the network, is y0, the initial y, minus the integral over the path taken by the examples of the expression above, right? And now we can reorder, right? We can change the order of the summation over the examples and the integral over the path, right? And we can take the average of the loss derivative over the path, and we get this expression, right? Y is the initial y minus the sum over the examples of the average loss derivative for the example times the path kernel, okay? It's that simple. So if you compare the two expressions, you can see what B is, right? B is y0. You can see what the AIs are, the average loss derivatives, and you can see what the kernel is. It's the path kernel as we defined it before, the integral of the dot product of the two gradients. So very interesting. Now there's a few remarks that I think are important to make. The first one is that notice that this is not a typical kernel machine as we're used to it, right? Notice that, well, first of all, the kernel here is learned, right? And most people are used to thinking of kernel machines with kernels that are predefined a priori, like a polynomial kernel or a Gaussian kernel. But there's actually nothing that says the kernel can't be learned. And in fact, there's a whole subfield of kernel machines that is about how to learn kernels. And you could think of, in this slide, you can actually think of deep networks or gradient descent in this form as another way to learn those kernels. Another aspect is that notice that the weights here, right, the weights can depend on the examples, right? And so can B, right? The B is the initial model, right? So let's set that aside. That's, that's just, it doesn't depend on any learning. Of course, it's just the result of the random initialization. Now, the coefficients depend on the examples, which is not what happens in a typical kernel machine, but crucially, they only depend on the examples through kernels. So if you take the most general definition of a kernel machine, which is a model where the examples enter only through kernels, this is 100% within that definition, okay? Now, if you don't like that, you can just use an alternate formulation, which is to absorb the loss, right? You can absorb the losses here into the kernel, and then, we call that the loss-weighted path kernel, and now the coefficients are just -1, okay? So you can also take it that way. And as we will see later, there's yet another way to look at it that comes from this, which is you can think of the neural network as just boosting the tangent kernel. So what the gradient descent is actually doing is equivalent to doing a series of boosting steps. So there's actually these three different but equivalent ways of looking at it. So notice that what I did here did not specify the loss function, right? So this applies to least squares for regression. This applies to cross entropy, which is what's typically used in deep learning for classification. It applies to learning a probabilistic model for a joint distribution by maximum likelihood or or using a Bayesian posterior or whatever, right? Notice also that what I just did here was for a pure unregularized loss function, but of course a lot of the times we do regularize the loss function. So you can ask what happens if there's a regularizer. What happens if there's a regularizer is actually very simple. Is just there's another term that gets added to B, right? So B here, in addition to I0, is going to have a term involving, not surprisingly, the dot product of the gradient of Y and the gradient of the regularizer with respect to the weights. So very very intuitive. What I did here was for batch gradient descent, which is the simplest and most well analyzed case. But of course, what we use in practice is stochastic gradient descent. And now the next question is, does this also apply there? And the answer is yes. What happens if we do stochastic gradient descent is that we have to multiply it, by an indicator function for each example that says whether the example is included in the mini batch at that step or not. So it's going to be a random function for each example over time that's going to be 0 or 1. And so what this means is that the integral now becomes a stochastic integral, which complicates the analysis somewhat, but the end result is essentially the same. Okay, and it's probably also the case that this result can be extended to most, if not all, of the many variations of gradient descent that people have come up with. Of course, how exactly to do that and which cases it will hold in or not is still an open question. Another interesting remark to make here is that this may have occurred to some of you, right? But this is related to the classic result for single-layer perceptrons of Eiserman, Braverman, and Rosenauer in their paper of circa 1960, I think, where they first introduced kernel machines under the name of the potential function method, right? So this is really the paper that first came up with this idea of using kernels for classification as opposed to just say linear models or whatever. And one of the things that they did in that paper that I always found very remarkable is they showed that the ordinary single-layer perceptron, which Rosenblatt had introduced a few years earlier, is just a kernel machine in our modern terminology, where the kernel is just the dot product. Okay, so these two things that look very different, kernel machines and nearest neighbor in general, and the perceptron, which is linear, very limited, actually turn out to be very closely related. And then the question, of course, becomes, can this be generalized to multi-layer perceptrons? And that's actually what this theorem is answering. 60 years later, is that, as it turns out, the answer is yes. This can actually be generalized to multi-layer perceptrons, and to many other things, like, for example, linear regression and and various kinds of regression and density estimation and so on. Another result that you may or may not be familiar with that is also very remarkable and related to this is that if you may remember this or know the history that neural networks had a big comeback in the 80s that was brought on by Hopfield networks, and then somebody actually proved that Hopfield networks are just nearest neighbor with Hamming distance as the similarity measure. And that was, Hopfield networks are, of course, more general than single-layer perceptrons. So that, again, you could say that this result is related to that, and also more, of course, it's a broader result. Now, notice, there's an important, caveat here, which is that this was all done under the assumption that the learning rate is sufficiently small. Okay, and this is a standard assumption in analyzing, learning by gradient descent. And it's usually a good assumption in practice because we tend to, particularly these days, because we tend to make the learning rates tiny, like 10 to the -3 or 10 to the -4 are common. Okay, so my guess is that this assumption will line up pretty well with what happens in practice, but of course, that remains to be empirically verified. So, what are some of the implications of this result? I think there are several interesting ones for both deep learning and kernel machines. On the deep learning side, one of the biggest things that people worry about is that deep networks are not very interpretable, and that of course makes them hard to use, hard to improve, hard to trust, and so on. But in the light of this result, we can actually now see that what a deep network really is just a superposition of the training examples. It's like it is indeed the kernel machine, except with a very clever change, if you will, which is that instead of storing the examples separately, I add them all up in the weights. But then because of the distributive property of the dot product, I'm still multiplying by each of the examples separately, even though they've all been effectively when I multiply by the resulting network, even though they've all been added together. So what a deep network really doing is just follows this diagram here, where the query goes in, I compare it with which training example using the kernel, and then I multiply each of those by a weight, and the answer is just a weighted combination of these kernels in this form. So something that's actually very intuitive and easy to understand. And if you think about how this relates to the ways that people have tried to interpret deep network predictions, probably the most popular method is to look for the nearest neighbors to the test example and say, the class that we're predicting for this example is some interpolation of the nearest examples in Euclidean space. But this, sometimes it works, sometimes it doesn't work very well, right? Because the prediction may not be the same that would be made by those neighbors. And now we understand why, and what you should be doing is that this idea of using the nearest neighbors to understand why the output is what it is, like, I'm predicting this is a cat because the nearest neighbors are cats, is a good one, but Euclidean space is the wrong space to do it in. The right space to do it in, at least if you want to understand what the network is actually doing, is the gradient space, because it is in the space of these gradients that I'm actually computing the kernels, as the theorem shows. Okay, so now we have a much better handle on understanding what the deep network is doing. We also have, I think, a better understanding of a lot of the empirical behaviors of deep networks that we have found puzzling over the years. So for example, in many domains from vision to language, it's been observed that the neural network often winds up behaving a lot like a kernel machine or like nearest neighbor, which seems puzzling because mathematically they look very different. But now we know that actually they are not as different as you might have thought. Another aspect, of course, is that we know that deep networks are very prone to adversarial examples because, and this has become a big area of research, and that's because when you move even slightly away from a data point, then the class changes dramatically, right? Or it can change dramatically because we're in very high dimensions. And for deep learning, this is puzzling. For a kernel machine, it's not, because this is actually what we know theoretically from first principles will happen to a kernel machine in very high dimensions. So again, a lot of the empirical behaviors of deep networks are now easier to understand. But maybe the most important consequence of this is for representation learning, right? We now see that this notion that the network is discovering its own features is maybe a little optimistic, right? Maybe it was always a little naive to think that like gradient descent, as simple as it is, somehow magically discovers new representations. And what we see now is that, of course, we are using a pre-existing feature space, just like we do in other forms of learning. The pre-existing feature space is just the space of gradients of a particular function. That's all it is. And the only thing that the gradient descent is doing is selecting. It's doing feature selection from that space. It's selecting which gradients to use at which points in order, in computing the output function. Okay. And one consequence of this is that we've certainly made a lot of progress in representation learning with deep learning, right? If you think of something very simple like principal components analysis or factor analysis, those are already in some limited form representation learning, right? They discover a new representation. And deep learning takes us further, right? Because again, the path kernel is a very powerful one, but it certainly doesn't take us all the way. So maybe there's a lot more research that needs to be done if we really truly want to do representation learning, which I think we do. And I'll touch on that again at the end. So what about implications for kernel machines? Well, one very nice implication of this for kernel machines is that now we know how to incorporate knowledge into kernels, and therefore kernel machines, in the same way that we've known how to do it for deep networks. Right? You could say that, so there's this notion that, deep learning is purely empirical learning, and that's what's so great about it. You don't need any knowledge, unlike in graphical models or symbolic learning or whatnot. But that is actually not the truth, right? The truth is that people, when they apply deep learning, they spend an enormous amount of time developing the architecture. And naturally, it's in that architecture that the knowledge is encoded. But it is an advantage of deep networks over kernel machines that you can encode that knowledge in the architecture, but not in the kernel, right? The kernel is almost always something very simple, even for sophisticated spaces, right? It could be a Gaussian kernel or a string comparison function or whatnot, something very knowledge poor. Whereas, contrast with deep learning, you can have a convnet that incorporates translation invariance and makes it very good for vision. You can have transformers that incorporate attention and so on. We can now directly incorporate all those things into the kernel by using the corresponding path kernel. So I can have a kernel machine that has the same properties for vision that convnets do, or a kernel for language modeling and question answering that has the same properties that transformers do. Another one has another implication is for kernel machines has to do with the curse of dimensionality, right? Kernel machines are more resistant than many learning methods to the curse of dimensionality, but not as much as deep learning. And now we can see why, and how we can make them more resistant to the curse of dimensionality. It's because the path kernel is actually a very clever kernel when it comes to combating the curse of dimensionality, because it's actually looking at things in gradient space. So to generalize from one point to another, they don't have to be close in Euclidean space, which is a losing proposition when it's high dimensional. They just have to have similar gradients. Think, for example, of the sine function, right? Y is sine of AX, right? If you want to do this with kernels in Euclidean space, you're going to need an infinite number of points because, Y is always changing. But if you do it in gradient space, you immediately generalize from any point to another one that has a similar derivative of Y with respect to X, which means it's very easy to learn because you just have, a sine function is just an endless repetition of the same simple function. So this dramatically reduces the amount of data that you need for learning. Now, maybe the biggest implication of this for kernel machines has to do with scalability, right? The thing that really always hurt kernel machines and still does, particularly in these days of GPUs, being used to learn deep networks and what, has always been their computational cost. Right? People came up with many ways to combat it, but the fact remains, learning kernels is expensive. It doesn't scale to millions or billions of examples. And there's two reasons for this. One is that the first thing that you have to do in a kernel machine is compute the gram matrix, so the matrix of kernels between all pairs of training examples, and that's already quadratic in the size of the data. And then you have to store your support vectors and match them to the test example at test time. And again, in high dimensionals, structures to do this efficiently usually don't pay off, so the cost winds up being linear or close to it. Now, with the path kernel, something remarkable happens, which is there's no quadratic cost to the gram matrix anymore because the examples are in superposition. So the cost of this is actually now independent of the number of examples, not quadratic, not even linear or log, it's independent. It's just a function of the number of dimensions because again, I added up all the examples into one vector of dimension D. And that class, and now I don't have to store the example, so that linear cost goes away in memory, right? Because I just have to store, the size of the network. Although to be fair, the size is so large that these days, it's comparable. And again, to apply, to compare, the test example with all the training ones, I don't need to do it with one example at a time. I can just, do this dot product in the path kernel space, which is a one step, which is O of 1 in terms of the number of examples. So this for kernel machines is very good news. Now, as I mentioned earlier, this also has interesting applications for other types of learning, which in the long run may even be the most important ones. So in particular, you can look at deep learning or gradient descent as boosting applied to a weak learner that is a tangent kernel machine. So if you take a tangent kernel machine, it's actually not it's an easy exercise to do, to see that each step of gradient descent is adding another tangent kernel machines to a weighted sum of kernel machines where the weights are the corresponding loss derivatives, and if depending on how you vary the learning rate over time, in particular if you the simplest case is where you keep it constant, but if you find the optimal one by a line search, which is often a very smart thing to do, this winds up being a form of gradient boosting. So surprisingly, you can also look at deep networks as just being a type of boosting. Again, another very interesting relationship to a very well-known and very successful and widely used type of learning. But of course, this applies to even other things. In particular, another remarkable consequence of this is that graphical models like Bayesian networks and Markov networks, if you learn them by gradient descent, are just kernel density estimation models, right? Of course, again, with a particular type of very clever kernel, different from the Gaussian and so on ones that we traditionally use, but graphical models are kernel density estimators. And going even beyond this, notice that no matter how you learn a model, if it's a convex learning problem, the result will always be the same, right? It's going to be the optimum, the global optimum that you are guaranteed to converge to. And we've just saw that if you do it by gradient descent, you get a path kernel machine. But since it's the same for all of them, we also know that any solution to a convex learning problem is going to be a path kernel machine. Okay, so much more general. And now we can ask ourselves, well, what if we learn things by even other methods? What about learning discrete models by hill climbing or some form of combinatorial optimization? And a conjecture is that those will also, at the end of the day, turn out to be kernel machines, which would mean that almost all of machine learning is kernel machines, which you could take as being bad news because it's not as powerful as we thought it was, and now maybe we need to find more powerful things. Or you could take it as being good news because it means that, well, hey, all it takes to learn is to great kernel machines are all unique, right? To use a very popular expression in machine learning these days. So to conclude, this, I think, sets up a number of interesting research directions. One is that, what I did here was analyze some existing model types and types of learning. But once you have this notion of the path kernel, you can imagine designing different learning algorithms from the existing both kernel and deep learning ones based on these ideas, and I think that's a promising way to go. Another thing to do is to think, well, why do we have to do gradient descent the way we have done it today, right? Maybe there's better ways to do gradient descent. If what they're doing is learning these path kernels, maybe there's more efficient ways to learn them. Maybe there's ways to learn that are less sensitive to local optima, et cetera, et cetera. Okay. On the other hand, if the conclusion that you take from this is that, well, gradient descent is not that powerful, then what you want to do is find better ways to do representation learning. And I think there are a number of worthwhile candidates. There's things like predictive coding, structure mapping, crossover, there's all of these different ideas, predicate invention and latent variable discovery, right? There are all these other ways of doing representation learning that we have perhaps been neglecting, but that maybe in the long run will actually get us, to truly powerful representation learning. But of all these, possible directions, the single one that I think is most exciting, the one that I'm actually working the most on, is this notion that what you're doing when you're learning is forming a superposition of the training examples, right? I think this is a very powerful notion that you remember the examples is a good thing, and then comparing them with a test example, maybe it is all that we can do, but you don't have to pay the efficiency cost of computing these similarity matrices and store them all and whatnot. You can superpose all the examples into one vector, whether it's of the weights of a deep network or something else. And again, if that's what you're going to do, why should it be done by gradient descent? There's probably many other things that you can do. And of course, there's that may work better, right? And learn more powerful models and be easier to learn and more efficient and so on. And of course, for those of you familiar with quantum computing or even just quantum mechanics in general, there's an interesting similarity between this and what goes on in quantum computing, right? Is that the whole point of quantum computing is that you get an exponential payoff by taking advantage of the fact that a quantum state is in general a superposition of an exponential number of things, and you're computing on all of them at the same time. Really, this is really the essence of why quantum computing is potentially much more powerful than classical computing. And you can potentially get the same type of gain here. So once you go from just storing examples to actually doing inference with them using logical rules and whatnot, the linear or quadratic benefit that I showed here actually becomes an exponential one. And now we know this takes things to a different level. And that is, as I mentioned, something that I'm working on these days. But there's many other things that you could do along these lines. Thank you.
Thanks a lot, Pedro. I think that for discussion, it would be better if you stop sharing.
Yeah, let me do that.
All right, let me try to put myself also in the spotlight. All right, so Pedro, thanks for the talk, and I didn't see this paper before, so it was interesting when you sent me the abstract of the talk, and I was wondering what are the implications for the two sides. And based on your talk, I guess it's positive for people that like to work with kernel machines, but not quite for people that like to work with deep learning, because other than the facility of understanding the learning, which comes in the XAI part, I don't see many other advantages with the kernel in terms of the network. But on the other side, for people that work with kernel machines, it's very good news, because you can calculate for giant data sets and expand. So I would like to see if this understanding of mine is correct, or if you see that once you have proven that they kind of are related, it's also positive for the deep learning part.
So certainly the kernel machine people have been very happy with this result.
Yep.
Delighted I would even like, because it's like, hey, kernel machines rule in the end, right? And I mean, also in terms of scalability and other things, as I mentioned, this I think is unalloyed good news for kernel machines. On the deep learning side, actually, it's more mixed.
Yeah.
So some people have been a little defensive, because you could construe this as a criticism of deep networks, like, oh, they're not that powerful. In the end, people have made a big deal out of them, and they're not. But that's actually, I think, not the main point, and not really the intention. Like, if you are a deep learning person, you should be happy about this result, because it gives you a better understanding of deep learning, right? Anytime that your technique is better understood than before, that's a gain, right? In its own right, and then because it also sets up the stage for making further improvements, right? And in particular, I think the gain in it, I mean, like the single biggest strike against deep networks across the board is lack of interpretability. And this, I think, is I would even say, like, probably the single practically most important consequence of this is that now you can have much better methods to make the outputs of deep networks and the contents of deep networks interpretable. So I think that's a huge gain. And from the point of view of representation learning, right? I've always been I really think learning representations is a central problem in AI, maybe even the central problem, right? And back when Jeff Hinton first started talking about deep learning in almost 20 years ago, I got on that bandwagon, if you will, because I was excited about representation learning, right? But the thing that I think we need to understand is that we haven't made as much progress in that direction as we would have liked to, right?
Yeah.
And I think if we convinced ourselves that we've solved representation learning when we haven't, actually, that's to the huge detriment of deep learning, right? I mean, if you go to ICLEAR, right, the International Conference on Learning Representations, right, which is now this, it started out as a little workshop and now it's this huge conference. The name is there, Conference on Learning Representations. But if you look at what the actual papers are, right, maybe a better name for the conference would be the International Conference on Applications of Backprop, right? Which, I have nothing against backprop, right? I spent this, this was basically studying it, right? But, I think there's something missing there. We need to broaden, right, the number of ways in which we try to learn representations. Things, this often happens in research areas, that things become a little too, they funnel too much into a couple of things. And I think too many people, and I have this ongoing debate with Jan LeCun, where he's a gradient descent fundamentalist. He thinks we're going to solve AI using gradient descent. And I don't think so. So deep learning, and ironically, I think Jeff Hinton is more on my side, right? He's also skeptical of backprop and has said publicly that we need to go beyond it. So again, backprop is a great thing, but I think it's actually good news for deep learning if this helps to open up the field to other learning algorithms for deep networks.
Yep, I agree with you. So let me try to formulate some thinking here, because I'd like to hear some of these from you. Many people in deep learning, they think that deep learning is the way forward for artificial general intelligence, because it's a rich way of finding representations. And they think that these representations really represent something and create new concepts and things like that. But you have shown here, at least for the traditional gradient descent, that it's just a superposition of points. So it means that you are not creating new knowledge, right? And this goes in the direction of the catastrophic forgetting. When you try to learn new concepts, you forget the others, of course, because you're getting new ways of looking at the points. So you're going to have other things superposed. So would you say that this theorem is one way of showing that we are really, really far from AGI and these rich representations?
Well, there's two ways to look at it. One is that, yes, we are very far, because look, so here's a very pessimistic way to look at things, is that we have spent now 70 years doing machine learning research, and we've really not gone that far beyond nearest neighbor.
Yeah.
Right? Kernel machines are a sophisticated form. I mean, nearest neighbor, when it was introduced in 1957, was in some sense the first true machine learning algorithm, because it was non-parametric. It was the first algorithm that could learn an arbitrary function given enough data, in sharp contrast to the models that people had before that, they saturated. At some point, you learned your hyperplane and you were done, right? And you could say that we haven't gone that far beyond that in all this time. So that's the bad news way to look at this. But the good news to look at this is that maybe that's all we need. Maybe we've overestimated what there is to intelligence, to AGI. And, if you have a sufficiently good, kernel machine, that will take you there. And in fact, there's a very famous book making this argument by Douglas Hofstadter, the author of Gödel-Escherbach, it's called, Surfaces and Essences. And the subtitle is Analogy as the Fuel and Fire of Thinking. And what he's saying in that book with his co-author is that all of cognition can be reduced to analogy. And I think the book is extremely insightful and penetrating, right? He hasn't been very successful in operationalizing it. But one conclusion that you can take from this, which a lot of psychologists, I think, would agree with, is that, yeah, that's all we need. So, the pessimistic view is oh, we're so far. And the optimistic view is actually, no, we're actually quite close, right? And to get back to what you said in the beginning, a lot of people think that deep learning is the way forward. The main point that I make in the master algorithm is that there are these different paradigms in machine learning, of which connectionism, aka deep learning, is one. But there's analogy. There's kernel, which is kernels. Kernel machines are one version of analogy. There's statistical learning. There's symbolic learning. There's evolutionary learning, right? And the point that I'm making is that each of these has a problem that it solves very well. So backprop solves the credit assignment problem, right? But all the others have problems that they also solve very well. So for example, kernel machines, our analogy, let you learn from one or two examples, which deep networks just can't do. So if you really want to solve all the 5 problems, you cannot but have elements of the 5 paradigms. So I don't think deep learning per se is going to get us all the way there. I think you're going to need, and this is what the idea of the master algorithm is you're going to need a learning paradigm that combines the important features, the important capabilities of these paradigms all into one. I'm also not a big fan of like having subroutine calls, the deep network calls a decision tree here that then calls. That actually doesn't get you very far, and the complexity blows up and whatnot. But I do believe there is a deep unification of all of them. And again, just look at this theorem, right? Potentially, they're all just kernel machines. So if that is the path forward, then I think this is actually a good way to make progress in that direction. Also, if you look at what has happened over the decades, right? Every decade, a different of these, the paradigms remarkably have been the same since the 50s, right? They haven't changed. But every decade, a different one is on the upswing, right? So, neural networks were the king in the 50s, right? And then they died for 20 years, and they were the king again in the 80s. And then they died again, right? The joke was that, NIPS should have become, BIPs for Bayesian information processing systems, and then KIPS for kernel information processing systems. And now they rule the roost again, but chances are, in another 10 years, it'll be something else. So it remains to be seen, right? And you were asking about, the catastrophic forgetting problem and superposition. Precisely one of the things that makes this superposition view of learning interesting is that it tells you how to learn compactly in one set of parameters without being hurt by catastrophic forgetting. And in fact, I was talking about how there might be better ways to learn superpositions other than by gradient descent, right? If you just go straight at that problem, what you want to do is say, how can I learn a superposition of these examples such that I don't lose information about any of them, or at least the information that I don't want to lose, right?
Yeah, but that introduces another problem, the problem of finding the correct points to let you do that kind of superposition.
It's an optimization problem, right? And I think in machine learning, a lot of it is figuring out the right optimization formulation. And then, we know how to do optimization, in all the different ways that I think that part is substantially easier. And again, think of just a simple example of the dot product, right? The one layer perceptron, right, actually does not suffer from catastrophic forgetting because I just add up literally all the examples with weights, right? And then when I multiply my test example by the weight vector, I am effectively multiplying, or do the dot product, right? I'm effectively doing the dot product of the test example by each of the training examples, and then adding up the results for each class and letting the one with the highest value win. So now the question is just how do you generalize this to multi-layer perceptrons or richer representations? And of course, we're going to have local optima and so on, but we're used to that.
Very good. I have here another question. Thanks for the talk, very enlightening. The question is, considering that neural nets are kernel machines, one of the implications is that there is an upper bound to the technology limited to the data points. Do you see a clear limit to the technology, and how far can we get using it?
I'm not sure what you mean by an upper bound, right? There are learning bounds in terms of what you learn given how many examples that you have, right? But those were there all along, right? It's just that deep networks are complicated enough that people weren't able to do that easily. They've done that with neural tangent kernels and do these types of analysis. But of course, the problem with neural tangent kernels, or one problem, is that they usually go to the infinite network regime, right? They assume that you have an infinite number of weights, which is a nice limit to study and to derive some theorems about what happens, in terms of, convergence and whatnot, but it's not realistic. The important thing to notice about the result that I showed in this talk is that it's not for the infinite, weight vector limit. It's for any architecture. and in particular finite ones, right? Now, how this will play out in terms of, the sample complexity of deep networks versus, other forms of kernel machine is a very interesting question that is, I think, to be explored.
Right. One thing that you showed here is that the proof is okay using the traditional gradient descent, and you mentioned that you can extend it to stochastic one. How do you see when you get things more complicated, like Adam, which is a combination of gradient descent and RMS prop, or other kinds of optimizations that include parts of the gradient descent, but not quite so?
Yeah, so Adam is obviously, a natural next thing to try to extend this to, right? And again, I haven't done it, so, just take these words with a grain of salt. But I don't think it's going to be that difficult. In fact, there are some papers by, Francis Bach et al. That have results that are in that direction, although not in this context. And the thing is that what Adam really is doing is combining. Adam at heart is actually a very simple algorithm, right? It's just combining the first order learning of gradient descent with the second order learning of the Hessian, or an approximation to the Hessian, because computing the full Hessian, the matrix of second derivatives would be too expensive. And in fact, that's not in this paper, but I've actually done that, right? You can actually just, in the same way that you're introducing the gradient descent, the gradient here, right? You can actually have a kernel that, in addition to using the gradient, also uses the Hessian. In fact, again, this is not published, but I have this notion of a Taylor kernel, right? Where what you actually have is any Taylor approximation to the function. You can actually view what gradient descent is doing as learning a Taylor approximation to the function at the initial point.
Mm-hmm.
And now you can add, so in a way, it's very interesting, because what successive steps of gradient descent do is actually analogous to having successively higher order derivatives, right? And so, so this, if you think about the following kernel, right? Like, I have a multivariate Taylor expansion of a function at a point, right? Which, of course, the size of it grows exponentially, the Hessian is quadratic, etc. But now I can define a kernel that is just the dot product of the components of the two Taylor approximations, right? And now Adam is a special case of learning with this. Okay, now, I mean, I glossed over a lot of details here, right? It's not quite this easy, but you get the general idea, right? So I think that a lot of those sped up, versions of gradient descent are all different variations on this, right? So there's actually a lot of room in this type of analysis to, I think, accommodate those variations.
Another thing that I was curious is this. You mentioned that when you have the regularizer in the cost function, it's just going to change B, and I agree with that. But there is another way of regularize the deep networks, which comes with the dropouts. So what are the effects of dropouts in the proof, in this formulation?
Yeah, so that's another good example. Again, I haven't done that analysis, but my guess is the following: is that it's actually quite simple, right? What happens when you do the dropouts is that certain components of your weight vector become effectively zero.
Yeah.
Right? When I drop a unit out, it's like setting to zero all the weights, right? That go from that unit to the following layer, right? And there is nothing that prevents me from doing that in the analysis that I currently have, right? What's going to happen is that if you look at the dot product of the two gradients at a given step, right? I can say, well, here, instead of using the full gradient, I'm just going to use the following components, right? Mm-hmm. I'm going to project the weight vector onto the subspace, and everything else goes through as before.
All right. Here's another question. Thank you for the great talk. How do you relate this view of superposition learning you showed with the XAI technique of influence functions, if you have heard of them? The ones that try to explain the model's decision through the training data. Have you looked at these influence functions?
I'm not sure which. I know influence functions in a different context, so I'm not sure which specific technique you're referring to. But as I alluded to, the way that this allows you to interpret the output of a deep network is very much in that spirit, right? Is by looking at the training data. Are you saying like, what are the training data points that are most influential in making the decision, right? And now you do some kind of interpolation between them, and that produces the decision. And that's why I made it. It's like saying, well, you know, like I diagnosed you with, you know, lung cancer because the most similar patient to you also had lung cancer, right? And he's the patient, right? But now the question, the key question becomes, in what space do I find the most similar examples? And that can be done through influence functions. Again, there's a sub-literature that deals with that, which presumably is what you're referring to. You know, I alluded to the very simplest case of just using Euclidean space. You can think of the path kernel as in some ways being the true correct answer to this question, right? We don't have to heuristically come up with an answer to the question of what is the influence of each example. We know that the influence is through the path kernel mathematically. So I would recommend using this. Now, there's of course a problem that I completely glossed over if you're going to apply this to interpretability, which is that path kernels are very expensive to compute. Right? So, but you know, you might be willing to pay that cost, but my guess is that you can probably compute something that is a very close approximation to the path kernel at a fraction of the cost, using a whole, you know, bunch of techniques that we're already familiar with. And at that point, this might look a little bit more like some of the existing methods, except, you know, with, you know, a somewhat deeper, more intelligent way of deciding what the influence of an example is.
Right. Two more questions. You said that we have decades of something that's more influential than others, right? And probably this decade is going to be about transformers. So how do you see these in these more complicated data-driven methods of transformers?
That's an interesting point of view. So let me make an analogy between what's happening with deep networks and what happened with kernel machines in their glory days, right? In the beginning, the big thing was support vector machines, right?
I remember I had many papers in which people asked me to compare with SVMs.
Yeah, exactly. You know, just the basic SVM. And then there was a second, so within that, you know, decade or a decade and a half of you know, very, very intense system and kernel machines, it started with support vector machines. And then it moved on, you know, to kernel machines. So that now things became more about the kernel and kernels for different spaces and more powerful types of kernel and learning kernels. And that gave it another, you know, breadth, if you will, right? And then structured prediction, something that I actually worked on a lot, right? Where now you're actually no longer just for classifying, but things like, you know, max margin Markov networks where you're learning to produce structured outputs like parse trees or graphs or even, you know, answers to questions and whatnot, right? So after the initial, you know, boom of support vector machines, there were a few, you know, sub booms from successive innovations, right? And then finally they ran out of steam. And I think this is what usually happens with most, you know, paradigms. And I think this is probably what is happening with deep learning today. So there was the initial, you know, like deep learning, people forget, like there was like the initial, you know, pre-training stuff that, you know, Jeff and others were working on. And then there was a period where it was all about sparse coding, right? I remember, like, you know, the early deep learning workshops, you know, people like Jan LeCun and Andrew Ng and whatnot, is like, you know, sparse coding is the key. And then there was the AlexNet era where things really exploded. That kind of like made those things, you know, be forgotten probably, and fairly so, right? But and the AlexNet was just, you know, good old-fashioned backprop with GPUs and a couple of, you know, and ReLUs and dropout essentially, right? And then after that, there have been you know, there was GANs, right? GANs were a big, you know, new thing, right? And then transformers are another, right? And I think there will probably be, and I know many leaders in deep learning who feel like deep learning is already running out of breath, right? You know, there's the critics like Gary Marcus who say it has hit a wall and whatnot, but even among the, maybe, I actually don't think so, right? I'm actually more optimistic about the near-term future of deep learning than many of the deep learning leaders, precisely, I mean, they see things plateauing, you know, we're reaching the amount of scaling up and extra data that we can use in large language models and so on and so forth, right? So some deep learning leaders at least feel like things are starting to plateau. And my thinking is that, like, they are plateauing, but usually after a plateau, there's another jump, right? So what my guess is that transformers, there's still a lot of broad impact to be had, right? So there's a lot more that can be done with transformers, but then they'll plateau, but then there'll probably be another, who knows what the next big, deep architecture will be, right? But then after all of that, deep learning will kind of run out of breath, and then you'll have to do different things. And they might be combinations of deep learning. Often the new thing when it comes along is not just going back 50 years, right? It's combining, again, the reason Bayesian networks and kernel machines both took off, at least in the NIPS community, is that they incorporated a lot of the things that people cared about in neural networks. So my guess is that it's going to be the same thing this time, right? It's not, some of the younger generation of deep learning folks often joke that they don't cite or read any paper in machine learning unless it's less than 3 years old or more than 30. So the question, right, and I think, Joshua Benjo made this point when he won the Turing Award, is that, like, what is the, currently obscure thing that everybody thinks is irrelevant that is going to be the next big thing, right? Because 20 years ago, it was, neural networks that were the, the dinosaur that nobody cared about anymore. Like, why would you learn networks when you could learn kernel machines? So we'll see what the next one is. Yeah.
We are running out of time, so I have one last question. With all of the experience that you have in the field, what would be the advices that you would give a student starting in the field? What are the most important paths to look for and what to expect in the years to come?
Well, we could have a whole talk just about this, but let me just say a couple of things, right? One of the most important things that I tell my students is, do not become, and relevant to the discussion that we've just been having, is do not become a man with a hammer to whom everything looks like a nail, right?
Yep.
There are a lot of people that grew up in one paradigm or another, and that's all they know. And then they go to industry and they have their hammer, and then they try to pound nails into walls with a hammer instead of screwing them in with a screwdriver. So make sure that you have a broad understanding of all the major different types of learning and how they relate to different problems, because that's how you will solve the problems better. Instead of wasting millions, sometimes billions of dollars trying to use the wrong thing and then slowly reinventing the wheel because you didn't know that that thing already existed, right? Slowly turning your deep network into a symbolic, to pick a non-random example, slowly rediscovering inductive logic programming in the guise of graph neural networks, for example, right? There's no need to waste time like that, right? Again, it's not to say that there's, good things happening in that way, but it's very important to have that broad. And when you do the PhD, it's very easy to get funneled into something very narrow because, you do have to make progress in something, but, spend 20% of the time just being curious about things and learning more, right? And another aspect, not unrelated to this one, is I think the best research is done when you have some important deep question that you really care about. It's not, some people do research, they do have a hammer, and then they look for nails. And there's actually nothing wrong with that, as long as what they find are nails, as opposed to screws that they try to pound into the wall. But I personally think that if you look at the researchers who really make a big impact in the long run, they're people who, like the founders of AI, right? They had a question that was 100-year, who knows, maybe 1,000-year question. So you should have a question like that you care about, whether it's to solve AI or something like, it can be more specific than that, or it can be different. But then with that question in mind, you go to every field on Earth to see what it has to offer you. And then it's by bringing together the ideas from these different fields to this problem that you will make progress that others hadn't. In a way, having that kind of impact is not that hard if you go by it this way. It's about not being narrow, but it's also not about just like randomly combining pairs of fields, because, who knows what will come of that. You combine them because they are both elements towards the solution that you're looking for. So I think that is another thing that I, highly advise students to do.
It's really good. It's like think about a big problem, a problem that can make us humans go one step further. That's really important. And just
Yeah,
not,
and also,
it's not like a publish or perish, because many people do that.
No, exactly. It's not about, MPUs, minimum publishable units, but, it doesn't have to be a big, gigantic problem for humanity, although like solving AI, although it could be, right? It can also be, for example, here's a heuristic that I follow and that I recommend to students that they follow is, I like to keep talking with people in industry, in different companies, in different industries, and in different sciences to see what are the problems that they have in common, that they don't even know that they have in common. You have problem A, he has problem B, she has problem C, but they all have a common sub-problem Z. That if you solve that sub-problem, you will help all these people at the same time, right? And then you go and solve that problem. And in a way, that's actually a remarkably easy way to have a lot of impact, because if you solve that problem, you will not just have impact in one field. You have impact in all the fields, all the industries, all the companies that all have that problem. And I've run it, many of my most impactful papers came out of exactly that. And I think there's a lot of scope to do that. And that's something that I recommend people do.
Really good. So, Pedro, muito obrigado por seu tempo, pela discussão aqui. Foi muito bom tê-lo aqui nas nossas discussões. Marcos, obrigado também por fazer parte da conversa aqui. Pedro, tudo de bom. Um abraço.
Obrigado, um abraço para todos.
Obrigado. Obrigado a todos que estavam presentes. Thank you very much, everyone who were present. Thank you. See you.